I'm Chee. I'm currently a research fellow at SUTD. And prior to being a research fellow here, I completed my PhD in SUTD. I also completed my undergraduate studies here. So previously, I graduated from the engineering product development pillar in SUTD, working in with a specialization in the robotics track. So I've done aero robotics research as an undergraduate. That got me interested in aero robotics, which is why I continued to pursue my PhD in this area. So during my PhD, I was working on the topic of lean sensing. So how do we use UAV to perform advanced tasks like autonomous mission with as little sensor as possible? Because we know that for drones or UAV, they have very limited battery on board the system, so they can typically fly for a very short period of time, so like 15 to 30 minutes. And then this duration get even lesser when you try to make it do autonomous tasks like do sensing and detection, move without human control in remote location. So my topic that is actually driven by a industrial project, which is a project funded by the Public Utility Board of Singapore, PUB. And this project deals with trying to use aerial robots to detect defect and do inspection in deep tunnel sewage system, or they call the DTSS. So this sewage system is more than 30-40 meters underground. So currently there's no means of inspecting the sewer system, because sending down a human is quite a problem. You don't want to put a human in such a confined space, in such a deep tunnel network. And this tunnel is also hazardous. There's a lot of hazardous gases, so you don't want to expose the human into. So this is actually a good application for aerial robots, because the aerial robot can fly in through the vertical shaft into the main tunnel and then do inspection in this long length of the DTSS. The DTSS is more than, like, I think 30-40 kilometer long. And then the UAV is able to fly back and out of the tunnel system. But the problem with this is that for the UAV to inspect a long tunnel section, it needs to have a very long battery life. So what we work on, or my research topic, is then to see how we can make the UAV navigate autonomously in this deep tunnel sewage system with as little power as possible. And here what you see here is like the iterations of prototype we have for this UAV, which we actually called the Surveyor with Intelligent Rotating Lens, or we call SWIR. So this SWIR, instead of using conventional LiDAR systems, so LiDAR are typically used in car-based systems or advanced aerial robotic systems, but they are very power consuming, because firstly the sensor itself consumes a lot of power because it sends high power laser, a lot of high power laser to scan the environment in 360 degrees. And then to deal with all these numbers that's coming out from the sensor, you need a very powerful computer. So when you put a powerful computer, the powerful computer also consumes power. So what we then need to see here is then, do we really need this powerful sensor? And then if we don't need the powerful sensor, then how can we reduce the amount of information? Because once we have lesser information, you can do all this computation with a smaller computer. Yeah. So what you see here is the prototype. Instead of using a single 360-degree laser scanner, which is actually not necessary in a tunnel environment, because in a tunnel we know that the tunnel have a fixed shape, which is a cylindrical shape. So there's no need to have 360-degree or millions of points just to know where you are in the tunnel. So instead of using like millions of points or a 360-degree sensing, we actually use discrete sensors. Like, these are the sensors that we use. It's called we call it a point of flight sensor, or it's actually a laser sensor, but it only senses in one direction. And to know where we are in the tunnel, or to know where we are in a geometrical shape, a non-geometrical shape, we only need about 6 to 8 of these sensors. So with these 6 to 8 sensors, it sees where are all the points, and it can extrapolate how the cylinder then look like, and then where the drone is in the cylinder or in the tunnel. Then the drone can use this information to stay at the center of the tunnel. Why do we need to stay at the center of the tunnel? Because the goal is not just to fly through the tunnel network, but also to do inspection. And if we want to do inspection, the camera needs to be at the center of the tunnel, so that we can see all around the drone, or see all the all aspect of the tunnel with a high resolution. Yeah. So here you see is the iteration of this system. This system was actually quite long ago when 360-degree camera wasn't a thing, or when 360-degree camera only has a fixed resolution like 720p or 1020 or 1080p, but in 360. So if you want to just take one small snapshot, it's actually a very poor resolution. So how we deal with this problem is to have a single camera. So here you see a single camera here. So as the UAV fly past the tunnel, this camera actually continuously rotates. So as it continuously rotates and the UAV flies forward, we can do a panoramic shot of the tunnel. So this panoramic shot can then be stitched together to form a super high resolution 360-degree image. And because we have also these sensors that I showed you earlier, that I mentioned earlier, to do sensing, so the UAV know where it is exactly in the tunnel, so we can also find out where each image is taken, so it will help in the stitching process. So here you see this went through the rail sewage tunnel, so with a lot of dirty stuff on it. And then this is a smaller prototype that we use to test all the system in the school, because we need to first test it in the lab in the school to make sure that everything is flyable. And then when we do this development, it's quite long, 3 years. And then finally, when 360-degree camera advanced, we decided to remove the rotating camera system, because this rotating camera system, while it provides very high resolution imaging, is actually quite heavy, and to design this is quite difficult because there's this rotating camera, and then because you need to have a rotating camera, you need to have a center shaft. And then you can see the drone is split into 2 parts, and all the wire can only pass through the center shaft. So it's actually a lot of electrical wiring inside, and we have data and we have power signal going through, so it produces a lot of electromagnetic interruptions. So there's a lot of engineering work needed to do this, and it's also quite hard to troubleshoot if assuming that this thing, something happened, because it's really it's very compact and condensed. Then we move on to changing the system such that it looks like this now. So instead of using a 360-degree rotating camera system, we mount a 360 camera right in front of the drone. And then because the tunnel is pitch black dark, there is a 360 LED system. So when lighted up, this illuminates the tunnel in 360 degrees to provide enough light for the 360 camera to do imaging. And we move on to use a more advanced version of this point of flight sensor. So now it looks a bit cooler, it's a full black. And then here you see an interesting light here. So this is actually infrared light. Why do we need this infrared light? Is because to navigate in the tunnel, while we use all these sensors can tell us where we are in respect to the center of the tunnel, or where we are in the tunnel, but we wouldn't be able to find out how far forward we are in the tunnel. So to do that, we use a very interesting technology called the optical flow. So this optical flow is very similar to your camera mouse. It's actually very similar to your computer mouse, because when you put the mouse on the table, you move left and right. Your computer knows how far you move left and how far you move right, up and down. So actually, the camera that we use is right from the computer mouse. So if you take out that sensor and put it onto the drone is able to tell how far forward it has been through the tunnel. But the problem with this is also we need lighting, because if you turn your mouse upside down, the very old school mouse that you use, there's a red light, but now they use blue light, so you can't really see it. So for here, because the camera is in front, so this lighting is insufficient to illuminate the optical flow camera. But if we add a separate visible light to it, it will kind of like overexpose one area of the image of the camera, the camera image. So what we do here, we use infrared light. So this infrared light cannot be seen by the 360 camera, but can only be seen by our optical flow camera, which is also the spectrum where the optical flow camera is very sensitive with. So with this, there's a 2-camera system here that doesn't interfere with each other. So currently, I'm working as a research fellow here, and my research area now is on the research commercialization or translation of existing technology that's in the lab, which is one of the technology that we are currently working on, is to commercialize a research project, the output of a research project that we have been working with a partner, which is the Land Transport Authority for cleaning of sheltered walkway using aerial robots. So currently, a lot of inspection or cleaning operation at heights require human, and then they use a lot of excess equipment like ladders, lorry crane, and cherry picker, so very heavy machineries to access this area for cleaning. But the problem with this equipment is that they are unsafe because humans will need to be at heights on top of this equipment. So as they climb up, it poses a hazard, occupational hazard to them. And then also deploying all this equipment is not really very efficient because you need to drive the equipment to site, and it's actually quite costly to rent and use this equipment for cleaning. So this is where using a drone or aerial robot is quite helpful, because with a drone it's a lot more portable, and then you don't have a human needing to operate at heights. The human is only on the ground operating the aerial robots. Yeah, so we remove the risks, all these occupational risks associated with working at heights, and it's a lot more efficient because we can deploy it anywhere, easy to bring up, easy to mobilize, more portable, and also more cost effective because the cost of the drone is much lesser than trying to own and use all this lorry crane and excess equipment. Yeah, so actually for the drone, first you need to have a licensed operator. So not everybody can fly the drone. And then in Singapore, there is a process of how to get yourself licensed to do this. So you need to be a licensed pilot to do this. And it's definitely a challenge because if, let's say, we have this solution and we want to deploy it for our partners, let's say this contractor, they need to operate the drone, they need to have a licensed pilot with them. So this is an issue that we recognize because this is an issue to adoption of UAV solutions. It means that anybody that want to use a drone solution to do cleaning or inspection at heights, they need to have a licensed operator. So that's a problem we also identified that we are trying to work on and solve. How do we make it easier for more inexperienced users or for new users to be able to operate this drone easily? So that's one. And then for the drone itself, we actually do spraying of high pressure fluid. So we don't do wiping, we don't do scrubbing. And this drone is actually quite advanced. It has a advanced camera detection, or a lot of cameras on board the UAV. And then it will detect where is the stain, and then it will automatically position itself to apply the fluid, the high pressure jet, at the correct location. So example, if we identify that there is some loose rust or some stain at certain part of the sheltered linkway, it will automatically position itself in terms of height and lateral position, and then controlling the angle of the jet nozzle so that it can apply the most effective pressure to remove the stain from the linkway. Yeah. Actually, the challenge of trying to spray fluid is actually quite challenging because when you spray fluid, there's a reaction force on the drone. So this drone wasn't developed in one step; it was developed in multiple steps. The first step is to first explore what is the effect of trying to spray fluid on the drone. So the first step we did was to develop a low pressure, a normal pressure water jet first. So trying to use the drone and try to spray some just basic low pressure water or water from the tap source, so to see what's the interaction effect and then how to design the UAV to manage this. And then the second step then is to see how we can then put a high pressure jet onto the drone and then study the interaction again to see what is the effect and where to better position this jet onto the drone, and then to see the interaction with the drone. And also a lot of one of the main thing is that because we are working with like Land Transport Authority to study how to use technology to make cleaning more advanced and safer. So definitely the goal of the project is to commercialize. So one thing that was quite challenging was definitely to deal with the vendor, because they need to be able to operate this drone and to see how this fit into the current operation procedure, and trying to minimize the steps to set up. And then I think that's quite challenging to see how we can then use how their existing workflow is, how they actually do cleaning now, study how they do it, and then to see how we can then adapt the solution into their existing pipeline. Okay, so this is the Blaster, which is the latest prototype that we are building and we are developing to do high pressure cleaning at heights. And what you see here, the special thing about this drone is that it doesn't have any battery on board or no water source on board. The reason is that we do not want the drone to be limited by the power, and the water source it can carry, because this will severely affect the operation efficiency. So what we have here is the drone, and then you can see there is two ports here, one for power and one for water. So the drone is actually powered from a ground power source and also from a ground water source. So this power is supplied to the drone, and water is also being tethered up to the drone. So with the current system, the drone can last for about 2 to 3 hours, way longer than a drone that carries battery that will probably only last from 15 to 30 minutes. And to do cleaning, the drone first need to know where is the stain. And to detect all these stains, it has a camera all around the drone, from the sides and to the front. So this camera system looks at, let's say for the case of sheltered linkway cleaning, it can detect where the stain is, and then the drone has a computer that runs a AI model. So the AI model actually was trained using some data sets to learn how the stains look like. And then, so once the camera detects that there's a stain at a particular location, the same set of camera is also used to localize the drone in 3D space. So it knows where it is in 3D space and how to then position itself to be able to better target and apply effective pressure to remove the stains. And what you see at the bottom here, this is the nozzle, and this nozzle is what emits the high pressure jet. Yeah, so it will apply high pressure jet at the location, and this nozzle is currently, it can be articulated, so it can pre-configure pre-flight. So if we are trying to clean a sheltered linkway, which is like a horizontal surface, we can configure it to point downwards. And if let's say we are trying to deal with cleaning of buildings, which is vertical surfaces, then it can be pre-configured to shoot forward. Yeah. So the drone is currently undergoing trials. So we are working with LTAs and their partners to see how we can use this drone to do with the existing processes, and trying to evaluate what is the value that we can bring to the companies that are currently doing cleaning in terms of time, safety, and efficiency and costs. And another trial that we're also doing is with Gardens by the Bay to see how we can use the drone to clean the super tree, to spray water, to spray chemicals. And the last area that we're also doing trial with is in the maritime sector, to see how we can use this to clean cargo holds in ships. There's a change in skill set. Firstly, in terms of the development of the drone, when we built the drone, it's definitely to make it easier to do research and prototyping. So a lot of the design is to make it easier for us to troubleshoot, change parts out, and then to repair and do maintenance. So that's the design philosophy when we design the drone for this kind of research and prototyping. Of course, when we want to translate into a commercialization, then it's very different, because now you need to look at how to design this drone, how to redesign this drone to be able to work in real world condition, in rain, how to make it such that it is tamper proof, because there will be a lot of people using this drone, and how they don't tamper with the drone equipment. Yep, and then how to make it easy to use, that's another thing. So in terms of the drone development, these are the different things that we need to adapt the drone to or redesign the drone to. And then in terms of skill set, definitely there's a shift, because we are researchers, so we do more, we deal with numbers, but these numbers are more technical specification, engineering specification. But then when trying to do commercialization as the company, you deal with different numbers, because now you have a product, but then we need capital to be able to do further trial, and then to have working capital for the company definitely. So now the numbers that we deal with is different. Now we need to look at the financial, how to price the drone, how do we model our growth, because one thing about getting working capital is fundraising, and investors, they ask a lot of difficult questions, which we cannot answer as a researcher. So the first step was to attend a lot of those bootcamp and accelerator. So that is where we got ourselves equipped with more financial knowledge, learn how to model the growth of the company, how to correctly price the product, how do we position ourselves to investors, where is our value proposition. So those are a lot of different skill sets that we need to learn, but luckily those are stuff that we can learn, pick up in a lot of accelerator, because a lot of accelerator are equipped to help engineers translate their skill sets or to relearn all these important skill sets that is needed to run a company or run a startup. Actually, for myself, long ago, I didn't see myself in engineering. I wasn't pursuing I wasn't interested in pursuing an education in engineering because I thought that engineering is very dirty, a lot of dirty lab work, which is something that I wasn't very particularly excited about when I was still in junior college days. But then in the end, I ran out of options. I don't know where to go, so I decided to pick up engineering. So, but that's the interesting thing. When I started to be a bit more open-minded, I got to SUTD. Then we learned a lot about engineering, about design thinking, and then about trying to build products. So the interesting thing is that I got a lot of satisfaction from trying to build stuff, because when we prototype, we actually get to realize a lot of our vision, our dream, that you envision what you want to create, and then to be able to then use equipment to create. And luckily nowadays, a lot of manufacturing technology are very advanced. You don't need to do a lot of manual, dirty engineering work. You have advanced machine like laser cutter, CNC machine, 3D printers, and those allow us to, or even allow me to do a lot of rapid prototyping to model and then see how we can better create the product. Yeah, I think then that got me a lot more interested into engineering, which I think is quite fun. You get to build stuff. You want to do something as your hobby, you want to build a drone, you want to make it into different shape, you can do it. And then to be able to access all this advanced manufacturing technology to build it, I think that is quite fun. And in terms of for young students and for students that are interested in STEM or not interested in STEM, I think the key thing is really to keep an open mind, try to explore and see what is engineering about first. Try to go to university, understand what do they do in the university, projects that they do. I think that will give you a different perspective on what STEM is about. It's really not about going to a workshop and then sawing wood or cutting metal. There's a lot more to that. There's the design part, which I find very interesting. How do you design something to customer specification? How to use the design thinking to translate user requirements into product features, how to then test the product, and then another more important part is how to iterate on it. Once you get a first prototype out, how do you then work on to be how do you then subsequently develop it to the second and the third one and the final one? Yeah, I think that is very interesting, and I get a lot of satisfaction from doing that, because for me, I'm someone that seeks instant gratification. Yep, so be able to have something in my mind when I think about something, when I design something on the computer, and to be able to build it the next day or the next week is something that delivers a lot of satisfaction. Yeah, so I encourage the students to explore this STEM, be more open-minded. Yeah.